In this video, we're going to try and work out how an operating system can maximize the use of resources, and you're going to find out about ways in which the user interface hides the complexities of the hardware from the user. We're going to look at processor management and a sort of variety of things that processors can do to maximize the use of resources. So an operating system can be considered from two viewpoints, the internal and the external viewpoint. So with the internal, you're trying to make the best use of resources available, whereas with the external, you're looking at the facilities that are available. So the internal is stuff like resource management, single unit scheduling, the optimum use of main memory and the best path for input and output transfer, whereas the facilities are the things that you learned in AS level. And that's your externals, okay, except for the resource management, which is going to internal. And with regard to the operating system structure, it's nice to think of it as user mode, which is in green, and kernel mode, which is in red. And so when it's all linked together, this is a layered structure for an operating system. The user interface interacts with the application programs. The application programs can interact with utilities and are serviced by the utilities. And then the utilities connect to the kernel. So for example, you might have a utility program which has to do some defragmentation, but in order for that to happen, it's got to speak to the kernel, and the kernel communicates with the hardware that is involved in the defragmentation routine. This is not the best way to think of or to structure an operating system. A much better way of structuring it is to use a more modular structure where the kernel can link to individual services, such as what is shown on the next page. So in this structure, it's the modular structure, we have the kernel, which runs all the time because it's in kernel mode or privilege mode. And what happens is that these different services, the memory management, device management, file management, and scheduling management, are all available to the kernel, and they can be called at different times, okay, whenever they are required. And this is a much more flexible approach to the previous layered structure, which requires you to use a utility program in order to access the kernel. So this allows us to be a bit more clever about how we manage the programs that are running with the CPU. And we're going to look at this in the next screen, which is all about scheduling different processes or programs. So in this example, it's all to do with time. Okay, so it's the time that the processes have with the computer or with the CPU. So we've got short-term, medium-term, and long-term processes, and this depends on whether the program is essential to the system, like a clock, for example, that's running all the time, that program, or more long-term like Hello World or Defrag or Super Mario. So these programs in the long term, they're stored on disk, and when they are required, they are moved into main memory. And once they're moved into main memory, they will be processed, or they'll be run through the CPU, or different parts of the program will be run through the CPU. But sometimes we'll run out of memory, and we'll start to use the virtual disk, for example, or the virtual memory. And at that point, we use the medium-term scheduler, to move that process back out to the hard disk if it's required. So short-term schedulers used for system resources or programs which are currently in memory. The long-term scheduler is used to move the programs from disk into main memory, and the medium-term scheduler is used to move it back from main memory out to the hard disk. So this section is talking about process states. So if we take one of our processes from the last screen, so the Hello World process, that's the one that spent most of its time in the long-term scheduling, so sitting on the disk until it was ready to be moved into main memory. So its time has come and it's moved into main memory. And it's about to be executed by the CPU. So before this can happen, the process that's been moved across needs to have something called a PCB, or a process control block. And this process control block is basically just a data structure, and it contains all of the information that's relevant to the running of the Hello World process. So when it's in the CPU, you've got different running states, different states of execution for that particular process. We've got new, ready, waiting, running, and terminated states. Now, if we just work through an example, I'll show you what happens with each of these states. So when the process arrives in memory, the Hello World process, what happens is that PCB is created, and the new process, creates the PCB, and then it's changed to the ready state. And once it's in the ready state, the CPU can give access to that process. And when it does gain access to the CPU, it changes from ready to running. And this means that the process is going through the CPU's fetch execute cycle. Now, at some point, another process might turn up and it might interrupt. So the clock might want to update, and at this point, the CPU determines that the interrupt, or the interrupting process, is more important, and so it changes the PCB from the running state to, not to waiting, but back to ready. Okay, so even though it's mid-process, the states are saved, the registers are saved, okay, into the PCB, for example. So register values or states, and then it's set to that ready state, and when the interrupt is finished, then the processor allows Hello World to reload its register states back in to the CPU, and it begins running again, and that running state is reinstated. Okay. Now, at some point, our Hello World might have to wait for another process to execute, and this happens with more complex programs. So if we're waiting for, say, a printer to finish outputting a page of A4 before the Hello World program can continue, the state changes from running to waiting. And this is different from when the process is ready to be processed, but it's just waiting for its turn. The waiting state announces that the process is actually awaiting the successful completion of a different process, and it'll have some data that is useful for the Hello World process. Okay, it's mostly called a waiting state, but it's sometimes also called a suspended or a block state. Once it continues running, and it will get to the end of that particular program or that process, and it completes execution, it changes to terminated. Now, this doesn't mean that it's been killed off or cancelled in some way. It means that the process has completed its execution. So to summarise, what is the purpose of an operating system? Well, the operating system has to provide facilities so that the different programs on the computer system can access the various hardware and software services that are available to it. And it does this through keeping a balance between all of the different processes that are running on the computer system and making it seem to the human user that multiple things are executing at the same time, where in fact it's just a very carefully controlled schedule using different processes in short, medium and long term scheduling, and employing interrupts to switch the CPU between one program and another. Now, you would probably recommend that you look into the variety of scheduling algorithms, or a couple of scheduling algorithms that operating systems might employ, such as first come, first served, or the round robin algorithm. There's also priority based scheduling, but that's a bit more complicated. But if you know more about first come, first served and round robin algorithms, then that will help you understand how the operating system manages to keep up that charade of multitasking.